RAG is absolutely blowing up. RAG this, RAG that. Companies are ragging everything. My boss even threatened to rag me, saying that everything I know can be put into a database and queried upon. Basically, that I am replaceable. So what exactly is RAG? Why is it coming for my job? And how can I build my own system with a retrieval-augmented generation?
But before we do that, I want to back up a bit.
Retrieval-Augmented Generation.
Yeah, or RAG, one of the most popular generative AI projects.
Hey, I checked him out thoroughly. Even gave up your hallucination, didn't you, John?
So, Retrieval-Augmented Generation is essentially equipping a large language model with a database. That's it. Think of this as a robot librarian. You ask the librarian, when was the Declaration of Independence? And the librarian checks the library and gives you an answer. In this case, the robot is the LLM, or AI, and the library is the database. So why would we want to do this? Aren't the LLMs designed to know stuff? Well, the problem is hallucination. It's when a large language model makes up some information that's not factual, but it just says it confidently. So you as a user go, oh, that doesn't sound right, but you're probably right. The thing is, we are generating billions and billions of words from these models, and we can't double-check every response. So brilliant people like this started looking at solutions around this problem. This is Edo Liberty, founder of Pinecone. He's built a specialized database that makes retrieval-augmented generation easy for LLMs. By the way, super cool name. Can you imagine this guy in politics? With a name like Liberty, his company raised $100 million. Talk about rags to riches.
Explain what Pinecone does.
I mean, when we think about AI models as being smart, they might not be very knowledgeable. And if you see all the issues that people have had with what's called hallucinations, basically AI models giving very smart sounding answers, but with wrong information, that is solved by equipping them with long-term memory, which is provided by Pinecone.
That's all great. But how specifically are people using this technology in business and for personal use? There's a Canadian IT company called Algo Communications that trialed a RAG-based customer service. And in 2 months, they were able to move 67% faster between cases. Their trial was such a success that now RAG touches 60% of its products and continue to expand. Using RAG has allowed them to cut their onboarding time in half. But the most impressive part, and this is a direct quote, it was going to allow us to break down a lot of those really complex answers and deliver 5- and 6-part responses in a way that customers knew there was someone technically savvy answering them. Here's how another company is using vector databases. Take a look.
With traditional drug discovery, less than 10% of human proteins are accessible to small molecules, usually because there are no traditional binding sites on the surface of the protein for a drug to bind. Frontier Medicine's revolutionary drug discovery platform changes that. Powered by chemoproteomics, covalent chemistry, and machine learning, Frontier Medicines discovers and targets novel non-traditional binding sites, or hotspots, on disease-causing proteins, including ones that are considered undruggable. Frontier Medicine's novel approaches to drug discovery boldly advance science to defeat disease.
If companies are starting to have success implementing this, what about the consumer or the end user? For that, we go to Notion. You've probably heard of Notion, or maybe you even use Notion. It's probably the #1 note-taking app in the market right now. Notion's CEO, Ivan Zhao, introduced the new feature Notion Q&A, stating that this is RAG for tens of millions of people. He thinks RAG is the future of knowledge management. In fact, he is really bullish on RAG. He says, RAG fundamentally changes knowledge bases in Notion. You may not need as much manual organization and can just dump information in and retrieve it. Everything moves to search. Now that I've hopefully convinced you that RAG is the promised land, let's talk about how we get there. The core idea behind RAG is very simple. The user asks a question. The system queries the vector database. Then once the vector database returns us some data, that data is sent to the LLM as additional context. The LLM generates the answer, and the question is answered. The only addition to the regular LLM request and response cycle is the vector database here. So how do vector databases differ from normal databases? In order to understand that, let's take a minor detour. One of the most important ideas in natural language processing has been the idea of vectorizing words. What this means is essentially taking a large corpus of words and running it through a small neural network, and assigning a vector to each word. So at the end of this process, you have a vector for every word, which is great. But the magic of this idea is that the vector that is assigned to each word starts to quantitatively measure the meaning of words, which means now we can compare words and see if they are similar or not. And that means we can do mathematical operations on these words, and we can code it so essentially computers can understand words. Note that while our visualization shows words in 3D space for illustration purposes, in reality we need word vectors that are hundreds or even thousands of dimensions. Now notice how when I click the word in the word cloud, other words also highlight. These are similar words. The reason we can do this is because, as I mentioned before, we can operate on these word vectors. For example, given a single vector and a set of vectors to test against, we can find other similar vectors. We can appreciate how the computer knows that man and king are similar words, as are queen and woman, or cent and Eminem, presumably from 50 Cent. And the beauty of it all was that no poor schmuck had to sit there and explain it all to the computer. The relationship between all these words to every other word, which in this small sample of 10,000 words would be about 25,000 semantic relationships, or 49 million all-out relationships. Vector databases essentially turn our text into vectors, and we don't just delineate our text at the word level. We do it in chunks. This could be paragraphs, it could be sentences or pages. Whatever we pick, it turns it into a vector. Then when a user types in a query like, "What is machine learning?" the database doesn't necessarily look for the exact match machine learning, it finds all related concepts, such as artificial intelligence or deep learning, and so on. Not only that, the database returns matches with similarity scores. Like I'm 90% confident that this chunk of text is semantically similar to your query, and a bunch of other search results in descending similarity score. Then the orchestration layer, or our system, probably our back-end service, puts it all together into a prompt. The large language model answers the prompt and returns an answer. That's really it. The revolutionary idea behind RAG is nothing more than a vector database and a special engineered prompt to an LLM. Why not fine-tune? Well, it hasn't been as successful. Of course it does work, it's just not as effective as RAG. Also note, people who have tried it are saying it helps with the rough shape of the LLM response, but not with hard facts. If you have money and want the best, and any small improvement is worth it to you, then you can use fine-tuning and RAG. And remember, the vector database will help you with both fine-tuning and retrieval-augmented generation. For version 0, let's do the simplest version of RAG. In here, we essentially use a website as the database or data source. Also note that we rely on LangChain to abstract away all of the actual implementation, so you don't know what's happening. You don't have much control. Nevertheless, this is very cool. The end result is a much more reliable and accurate answer from our LLM. Or it should be. But as you can see from the website, the right answer should be one of 512 or 1536. Ideally both, but it's not. So we're not satisfied. For version 1, let's try this. This is production-ready RAG, but built under an hour. At least that's the spiel. So I tried to install this for exactly an hour, and the Docker image just wouldn't work. The system wasn't living up to its promise, so I decided to move on. Very disappointing, but what can you do? The reason I think the Docker and Make are so complicated is because it actually has a lot of components inside it, like the core library, which has more components, the server, the CLI. Also, I realized eventually I would want to build the RAG into my existing backend, not add another service to my setup. Overall rating, 1 out of 5, would not try again. Version 2, this is the real deal. But before we do this, let's quickly review what we want to accomplish exactly. By now, we're very clear on what we want. We want to simply ask a question and get an answer. which would be the retrieval and synthesis stages. But before we do that, we need to fill our vector database with data, which would be the data storage and embedding stages. Let's do the data ingestion first. Let's find some data. Something kind of useful is documentation or product update websites. So we will use the OpenAI website as our data source. For the most part, this is actually a lot easier than Canopy. I learned that when you do something expensive like embedding a piece of corpus, you want to store the chunks and vectors in a data frame and store it manually in your drive or computer. Just in case, you make small errors and you have to keep rerunning your notebook. Before I delved into the data ingestion part, I needed to build a working script for the vector retrieval sections. This whole process took me about 3 hours to set up, but basically, now I just need a large piece of text and a search query, and that's all I need to do semantic search, which is pretty cool. For a super basic test, I added a paragraph of 3 sentences and chunked them into sentences. That means that each sentence turns into a vector. My reasoning here is that since the second and third sentences have the word sentence and the word phrase has a similar meaning, those sentences should show up first. And it does. In fact, if I search phrases, not phrase, the semantic search returns, it has many sentences, showing that it understands plurals. Now this isn't particularly a RAG because it's missing the LLM piece, but that would be relatively easy to implement. Prompt it with something like this, and you're set. But let's move on to RAG version 3. For version 3, we obviously want to improve upon version 2, fix some of its main shortcomings. First, we got to work on the data ingestion part now. The other thing we have to consider is our use case. Something that's useful that I want to do sometimes is talk to a documentations website, ask it questions, or updates to APIs and such. I tried using Notion, but it doesn't work right away. For example, I copy and paste some new topic into Notion. Then I ask the Q&A chat, and it doesn't have it indexed or upserted. I asked Notion on X, and they say it's usually about 30 minutes or less. So features for this one: ability to insert large text, ability to use URLs, ability to ask questions right away. First, I needed to insert a URL, and then the system grabs all the text from it. Turns out it's not that simple of a task, because every website uses a different setup, so no system will cover 100% of all use cases. Also, you can always grab all of the text and use a large context window LLM to clean it up. However, that can rake in the cost. So I wanted to do it old school, regular programming. However, that proved very annoying and difficult. But thanks to Beautiful Soup and NLTK, I was able to grab perfect English sentences out of most websites. Also, it can grab information out of tables, given that it's a properly formatted table. The key to being able to do this was to grab the text out of every P element, then reconstruct it back into a single string, only to sentence tokenize it back into proper English sentences. As for tables, the key was to create a list of lists for the table data, then crush it into a single string and sandwich it between 2 commas to trick the tokenizer into thinking it's a proper sentence. Then I realized there are even better tools for this, so just hang on. So in summary, version 3 you can basically enter any link and ask it questions. Before we move on to version 4, let's talk briefly about MTEB. MTEB stands for Massive Text Embedding Benchmark. It's a ranking system. It ranks embedding models. It aims to assist in selecting the right model for the right task. It tests over 30 models, utilizes 58 datasets across 112 languages. OpenAI's text embedding 3 large is 13th position overall. Performance varies by task. No single model excels at all. For example, SimCSE performs well in semantic similarity, but not in clustering or retrieval. MTEB is open source for easy access and evaluation. Make sure you change tabs to check which models is best for your use case. For my example, I'm not using the best one for retrieval, but that's okay, because this is just a demo. Eventually, I will use the best one for retrieval, which right now is a Mistral model. For version 4, let's improve on the main shortcomings of version 3. Our version 3 basically could handle very short text from a single source. The reason is because it doesn't optimize the upsert throughput. Pinecone suggests that we upsert about 100 embeddings at a time when we are loading the DB, so we will fix that. Also, it's important to see how RAG can fail. Normally, you know a RAG is not working if the information you get is wrong and you know it. But how can it be wrong? There are two cases. Missing information. Wrong answer. Either way, you get bad answer. So let's think about it in a funnel sense. The first stage of the funnel is the retrieval from the vector database. The information retrieved can be irrelevant, or be missing even though you know the information should be there. You can mitigate this by using the best embedding model for the task, which in our case would be retrieval. The second stage is the synthesis stage. Here, even though you give it the right and complete information, the LLM still messes up or hallucinates. You can mitigate against this by maybe doing sample and vote. What about how you filter out the vector DB responses? For example, different top K or using above a certain threshold in score. The easiest wins, cleaner data, bigger chunks, and we will talk about some advanced methods in a bit. Also note that a really good way to up your reliability is to add a few easy and simple validations on incoming requests. For example, if a user sends a large text, it is much better to handle that yourself rather than sending it off the LLM and having it reject. Because you could cut off the context yourself or deny the request with a helpful message. So let's start off by using the large embedding model and larger dimensions, which means larger chunks. The token limit is about 8K for this particular embedding model, which is text embedding 3 large. Token limit is about 16K for LLMs. So if you have chunks of about 4K, then you can safely fit at least 3 chunks. Therefore use top K of 3. Now I'm pretty confident that the RAG can answer almost all questions by now. But it kind of fails to answer meta questions, like what's this document about? So if you refer to our earlier model of how RAGs can fail, it is right now giving me partial answers, and it is not completely satisfactory. However, after using the bigger chunks, it gives me correct answers. But here's my reasoning. I want to have smaller chunks, because by fitting more number of chunks, instead of one big chunk, the database can rank relevance more granularly, and this will only grab relevant bits of information across the entire corpus and give those as context to the LLM. Whereas if you give larger chunks, the LLM has to process a lot of unrelated context. I think is more apparent with smaller models. Next, I had to experiment with a bunch of values. The variables I could experiment with were chunk size, which I measured in sentences. The other cool thing that all vector databases offer is metadata. They basically give you a metadata that you can attach to every vector. So you can try adding additional context through this metadata. I thought I would experiment with text source, adjacent sentences, summaries. At chunk size 3, I got incomplete answers. At 1 or 2, I kept getting IO rate limit exceeded error. If I add previous or next sentences, then the metadata size limit exceeds. At chunk size 5, I am getting good enough context size while also being small enough that I can get multiple top K results. This seemed to be the sweet spot. Now I am getting really good results because of something I did, which is pre-query LLM call. Basically, I asked the LLM, here's a user prompt. What word should I query a database with to get user's intent? I thought that since we embed the user query into a vector, before we query the vector database, how do we know that some of the words just add confusion to the embedding model? Like, is it paying attention to the right words? So what better way to use attention models, which are all LLMs, to extract the user's intent? Then use those keywords to search the vector database, and it worked out really well. For version 5, I thought I will throw everything at it, within reason. And going back into one of the earlier steps, which was the ETL pipeline. The best way to improve your RAG system is to have the best data, and that means extracting the best data and retaining all that information, whether it's a text document, a spreadsheet, a web page, a PDF, a Git repo, or hundreds of other things. There's likely a loader for it. Be careful though, because not all loaders are created equal, and some load more content or context than others. What are some other creative ideas to give your RAG the edge? You could give it data from any kind of database really, as long as you have API access to it. This means you could even load it with transactional data from SQL tables, given that you handle identity access management properly. What about prompt optimization? Here's a simple one to start with. Now we're ready to talk about several brand new ideas. Extending the metadata size limitation. You could store references to some database object, store it in your favorite SQL or NoSQL database, and then now include this giant context with your giant token limit LLM. The only caveat here is the extra milliseconds it takes to query the DB and maybe process the longer context for the LLM. Next, there's this idea of a corrective RAG. I took some of its ideas and implemented it. So let's get started. Let's start with the red. We want to route. So for routing, I really care about these features. Big context length, cheap, fast inference, high quality. Price and quality can really fluctuate depending on the task too, but either way, every incoming message goes through a classifier and gets routed depending on the complexity of task and availability of data. Speaking of speed, the need for speed, I want to use Grok. If you don't know what Grok is basically the Tom Cruise of inference engines. It's a really fast inference engine for large language models. Blue section. So for this section, what needs to happen is actually retrieve the data, and if there are no returned values or scores are really low. Then we fall back to web search. Again, simple but powerful. Finally, the green. This one is more like a quality assurance on a response. Basically a post-processing on a response. Try to catch hallucinations and check if answer has actually been answered. Some critical pieces of data are things like numbers and links, so you can quality assurance that the LLM didn't just hallucinate and fib some of these. So let me refresh your memory. I have already upserted a single page into the vector database, and it is working pretty well. But now I need to basically ask it 3 types of questions. Related questions, totally unrelated questions, really complex but related questions, and ideally pass all of these tests with flying colors. It's also important to track and trace which path the request takes, since our code is just slightly more complicated. In the post-processing step, what are some important things to do? For one thing, we can verify source citations and numbers. Since these are highly important bits of information and easy to check, we can always do that first. And it is done basically by doing an exact match search. And while we're talking about tools, Pinecone isn't the only name in town when it comes to vector databases. Here are some others: Weaviate, Vice, and Chroma. If you've used both Pinecone and one of the other ones, and you think the other one is better, please let me know why. Also remember to remove personally identifying information from your responses, especially for production environments. To remove PII, you can apparently use tools like these. I haven't tried it out yet, but I'm sure it works. Also, did you know you can use your own embedder here? I don't know if embedding models have attention mechanisms, and I would love to learn to make my own one day very soon. So let me know if you guys want me to try that. Another interesting idea is to fine-tune my own model. See how difficult that is. In the next video, I have found this one book about building knowledge graphs with graph databases. So I think that's what I will do. Now that I know the basics of vector DBs and graph DBs, I will do a comparative analysis of both, and maybe build a combined system. Something else that's in the pipeline is revisiting